Hello, welcome to Introduction to Arduino Program, the second lecture of Digital Design and Embedded Software. I'm Alison Griffiths here again, and my contact details are given here. Before I go on any further, if you would like to, if you like reading books on whilst you're learning, an excellent book that is useful for this course is Beginning C for Arduino, 2nd edition. So it's helping you to learn C programming, especially for the Arduino. However, we will be using generic C programming in this course also. There are lots of extras online, so these can be used in tutorial and help you and aid your learning further. Some of these extras have been used throughout this course. So the overview includes the basics for getting up and running with an Arduino board. You will become familiar with the software, hardware, and the concept of writing code. As we previously mentioned, then pin 13 has a LED already built into the board, so that's usually the first program people write. So the installation of the Arduino software is extremely easy. It's open source software and it's one of the absolute best things about the Arduino, how easy it is to get started. The software is installed onto your computer and is completely free. So it's ideal for students and concept design. And the program is called the Integrated Development Environment, or the IDE. I did mention this in the last lecture, and it runs just like a text editing program. The most up-to-date installation information is available at the Arduino Getting Started webpage, or the homepage. You will find that there is an awful lot of information at the Arduino homepage. If you are on a computer that doesn't have the IDE installed, then you can create an Arduino project here using the web editor. However, this may be problematic if you don't have connection to the web. So the first thing you want to do is to create an account with Arduino. The tutorials homepage is here, and there are example projects on this hub and also built-in tutorial examples. So if I just click on the built-in tutorial examples, with the IDE, all these tutorials are already built in. So you go to File, Examples, and Tutorials. I'm now just going to launch the IDE from my computer, Arduino. And as you can see, I've got lots of programs called Arduino. So if I just change to Apps, then I go to Arduino IXE. Then this will load. I'm just going to minimize this here. So I've got 1.8.5, and I know that this is an old version. It says that the COM port that the Arduino is connected to is COM port 4. This is extremely important when you're actually running your programs. So I was talking about examples. So if we do File, Examples, then you can see there are many built-in examples. So we've got basics, digital examples. So if I open any of these examples, then let's just do basics, then the code is already there. You will need to connect the components up also for this. However, you could run this by uploading this code direct to the board. Before you do upload it to the board, you do need to connect the board to the right port. And at the moment I don't have an Arduino plugged in, so you can see that port is grayed out. in another lecture, I will show what happens when I do have an Arduino board plugged in, and therefore you will be able to see what happens. Okay, so for now we'll go back to the PowerPoint. So there are lots and lots, there's a huge wealth of Arduino informations out there on the internet. This is just a small list. You will find many examples and many more examples throughout my material. So Arduino beginners on instructables. Here's another link for microcontrollers. So useful beginner circuits. Just going to click on this one. So it gives you all sorts of circuits that you can build in an emulator. So what's an emulator? An emulator is a program that's available on the web that copies the notion of real hardware. So the emulator that I'm going to use is Tinkycad. These circuits were all built in Tinkycad. And a lot of my circuits are built in Tinkycad that I'm going to share with you. And you can see these things running here. There's a video of the circuits on this web page. So if you can connect these circuits up, copy this code, and then understand the code, and you can then be up and running just as quick. So Tinkycad Emulator is here on the web. I'm already logged in, so this is my dashboard for Tinkycad. Here we have circuits, and I have lots of circuits that I have created. And I can create a new circuit. Where if I have all the components, I can have Arduino starters. So I can have breadboards. These are my examples in Tinkycad. So I can install these. I can have more than one. If I want to view the code that is on these, I mean this is just a quick demo. If I want to view the code that is on these, then this is block code. I want to see the text code. And I can switch between the two Arduinos. This was Arduino 2, so I'll switch to Arduino 1 and I want to see the text again. So I can see the code, I can run the code, and I can see what's being printed to the serial monitor. This is a quick overview. You will very quickly get to understand what the serial monitor is and other things. So if I get rid of the code and I start the simulation, then this one fades the LED in and out. So we're varying the voltage at pin 9 to vary the brightness of the LED. In this particular one, I'm guessing that when the button is pressed, then the LED on the board L is on and off. So here you can see the brightness. There are oscilloscopes, and in fact if we look on all components, then there are lots of components here. Sensors, different types of sensors. Again, sensors, digital inputs, so keypads, outputs, lights, neopixel rings, motors, DC motors, encoder, micro servo, servo motors, hobby gear motor, piezo buzzer, 8-segment display, LCD display, batteries, breadboard. We've got the Arduino, and we've got multimeters, a power supply for the high power examples, got function generator, and we've got an oscilloscope which you will use. So we've got standard IC chips. So we've got 555 timers, two separate timers on a board. So you can sometimes do some of the things within the software, and you can implement, or you could implement them with hardware. We've got operational amplifiers, we've got quad comparators, we've got dual comparators, optocoupler. Here we've got different transistors for power control. We've got MOSFETs, relays. We've got regulators, 5-volt regulators, relay, again, simple motor controller. And then at the bottom, we've got the H-bridge motor driver, which I mentioned in the previous lecture. Wi-Fi module. We've got different connectors. So we've got a USB connector to wires. Not used that one yet. Might be useful for a future project. I am zoomed in quite far. Well, good thing about this is it does tell me what each wire is. Then we've got a variety of logic gates, Schmidt triggers, and all sorts of ICs, integrated circuits, D-type flip-flop, 4-bit latch, 4-bit adder, 4-bit binary counter, 8-bit shift register, decade counter, 7-segment decoder. So with all of these components, you can see that you could build up many different projects and try them out in software before even picking up a piece of hardware. Why would this be useful? Well, if we're in a class, I could ask you, well, if you wired the circuit up wrongly with actual components, then you could fry the board, you could give yourself a bit of a shock. But here it's all very safe, and if you do make a mistake, then it will tell you. So there's my quick introduction to Tinkycad. So there are many constants in the integrated development environment, IDE, high and low. So we've got high logic level, so 5 volt out at a pin. Low voltage level would be 0 volt out at a pin. True and false. So A and B. So if A is 1 and B is 0, then A and B would be false. If A was 1 and B was 1, then the answer would be true. So general purpose GPIO, general purpose input output configuration. So pins on an Arduino can be input, so waiting for a push button or a sensor value. They can be output, so they're being monitored as an output, or they can be input pull-up. So a resistor can be used when it's input pull-up to protect the board. Numbers can have take all different formats, and these are these are how we differentiate. Binary has a capital B, and then we define the byte. So it's 1, 2, 3, 4, 5, 6, 7, 8. So that's 1 byte. Signed integer, because it's minus. We can have an unsigned long. So this would be 2 bytes long. This is hexadecimal. So 3C in hex, and here we have an 0, 1, 2, 3. So whole numbers can be in different number formats. Floating point, obviously, where the variable is not a whole number. So minus 1.2, 1.7 exponential to the exponential 5, and minus 62 times 10 to the minus 12. So it's an extremely small negative number. So why do we have different data types? Well, the memory of a microcontroller is very, very small. So what the designer would like or needs to do is, when they're defining their variables, then to use the smallest data type possible. So imagine you're using a couple of bits and you use, say, a long integer. So that's 32 bits and only a few bits are being used. So an assigned integer, or a C, is a 16 bits. So 2 bytes. 6, 8. So 16 bits. A long int is twice of that, so that's 32 bits. A char, which is the smallest, is only 8 bits. Whereas if we say, oh, we're not worried about what we define, if we just define everything as a float, if you defined everything as a float, some of your variables would be 4 times, from 8-bit to 32, larger than they needed to be. So it's important to define the right type of data as the correct data type. Unsigned int, so if you if you're not bothered about positive and negative data, then you use unsigned. That means that you can use the most significant bit as another number. So you've got unsigned int, unsigned long int, boolean, true or false. So these can either be 1 bit or 8 bits. A double is 32-bit. Word, 16-bit, unsigned. Byte is 8 bits, unsigned. A string, 8B star. So there's 8 bits per character, so per letter in the string. Similarly, an array, it's 8 bits times the number of elements in the array. We'll be looking at examples with all of these data types later on in the lecture. Short is also signed and 16 bits. An unsigned char is 8 bits. A string can be any length. And void is 0. Void is what we put when a function does not have any inputs or does not have any outputs. And we'll be talking about functions later on. Either functions that you write yourself or that have been pre-written. So, I/O functions. So there are certain functions, these functions are written already for you if we choose to use them. We'll be talking in the latter lectures of how to not use some of these functions to enable our programs to work more optimally or in a faster way. So pin mode basically defines that tells the Arduino, is it an input pin or is it an output pin? And also, does it have an input pull-up resistor? So pin mode should be applied to all of the digital pins, which are denoted in blue, and the analog pins. It is thought that if you do not always define the pins that you're using, however, if you don't, there may be some issues. So digital write is write a 0, a high or a low, so a 5 volt or a 0 volt to a particular pin. And digital read is the opposite. So this is when this is an output pin. When this is an input pin, you would use the digital read in your program to say what value is, or digital read, is that pin high or low. Tone is output a specific tone or a signal with specific frequencies to a particular pin. No tone, stop the tone. Pulse input is a pulsed input with a specific, that should be the same height, pulse width ratio. Analog reference, so we looking at analog now, so we can read in from the analog pins and perform an analog to digital conversion, and we can write out to the analog pins. Interrupts. So quickly moving on, we will talk about interrupts in a lot more detail later. This is just to tell you what an interrupt is. So in your Arduino program, you have the setup loop, and it goes through once, and then the main loop. So that goes through infinitely. However, in your system, there might be something that happens that says, if there's an emergency and the button is pressed, the emergency start button is pressed, then switch everything off. So in this case, you would need a hardware interrupt or a push button. So emergency stop. You have to attach interrupts and also detach them, and you have to enable interrupts. So interrupts can be hardware, they can be software, they can be timer, and they can be pin change. Interrupts need to change a variable in the main program, because what happens is when the interrupt occurs, control goes over to the interrupt for a period of time and then comes back to the main loop. So if there's a condition in the main loop that does something once the interrupt has happened, and then does something else if the interrupt happens again. However, we will go into this in more detail later. So here we have Arduino bits and bytes. So if we've got a byte of data, like I had in the previous slide, 1, 2, 3, 4, 5, 6, 7, 8. So here we have the least significant bit and the most significant bit. So obviously the low byte is this one and the high byte is this one. You might want to read an entire byte or read the contents of a particular bit. So this would be bit 0, 1 to 7. So 0 to 7. And set a bit or clear a bit. So we've got some logic. So A and B, A or B, and A, X or B, implemented in, well, with Arduino, with hardware, so with integrated circuits, and also we've got it implemented in software. So here we have the circuit where we've got the Arduino. Don't expect you to worry about the actual coding of this yet. By the end of this lecture, you will understand most of this anyway, but we'll just talk about it here. So we've got inputs, so 2 potentiometers, analog inputs. Once they get over a certain threshold, then they will become logic 1 on this output pin here, so pin 5. And then these are the 2 inputs to an AND gate, an OR gate, and an exclusive OR gate. So if you look at this in hardware, so you can, this is a public link. You can click on that link, and if I'm going to say tinker this, you can just simulate it. I'm already logged in, see? So if I say tinker this, so if I stop my simulation, at this point I'm not going to go through the code, but I can see, I'm just going to move that. When both inputs are off, then nothing's on. If I put this one to a maximum, this LED has come on. And both OR and exclusive OR chips, can look up these chips on the internet for their specs, are the quad chips for OR gate and a quad chip for XOR gate. And here we've got an AND chip. So A or B is both on. If I increase this one to, just need to move up a little bit. Switch this one on, logic 1. Then my A and B is on, my A or B is on, and my A exclusive or B is off, and that's the correct operation. So let me stop that simulation. The code for this is here, and as I say, I'm not going to go through this particular code yet because we're going to do that later. So if we do the same thing in software, or something similar, I've got an AND or an exclusive OR calculator here. This particular example is interesting because we only use 3 pins for 8 bits output. So this time I'm using a 8-bit shift register chip, or the 74HC595, and 3 inputs from the Arduino, which is the input, which is the data, the output clock register, which is on pin 5, and the shift register clock. So every time this tells the program when to shift. So I do need to see the code here, because in this particular program I not only see LEDs on the output, so these are connected to the different outputs. Output, I think this is the first. Output 1, and then this one finally to output 8. So this is the output 1, which is the least significant bit, and this is the most significant bit. When I click on my serial monitor, again, I'm not going to go through the code for this. You may want to do it later. So if we start the simulation, so LED map is a number, 240, that we are going to exclusively or a number that we are going to input, and the output is going to be shown here on the serial monitor, but also in the LEDs. So if I say 0, then it will take a little bit of time. The AND result is 0. The OR result is 1, 1, 1, 1 and 4 zeros. And the exclusive OR is the same. So if I say 2, 5, 5, so that should be represented in binary by all ones. So there we have it, all ones. And the AND result, I missed it, but the OR result is all ones, and the exclusive OR result is the first. The least significant bits are on. So if we do 255 again, because I missed it. So we have the upper 4 LEDs or bits. The OR result is all of them on, and the exclusive OR is this appears to be the most significant bits. However, the leading zeros here are not there, so it is the least significant bits which are there, but don't be fooled by that. The other thing is if I write 256, then it's saying this isn't the correct number. If I write a letter, it's also, does it work? No, it doesn't work if I do a letter. So the code is, we define the pins up here. This is the what we're ANDing with. This is the LED map. I won't talk about this code now. We will talk about code in more detail and maybe come back to this example later. So that is logic in software, which gives us, so you can see in hardware we have certain features in the first example here, and in software we have other features, and it's extremely useful in the Arduino because we're only using 3 wires or 3 pins rather than 8 pins, because if we were using 8 pins to do the same thing, then we'd soon run out of pins. So the other examples are a shift register. So there are functions predefined called shift in, shift out, and serial. We've just seen an example of the serial monitor. So I'm just going to use, it's the same circuit diagram, exactly as the logic in software example. But for the shift register, what we're doing, this is used to store data, like when you've been designing not circuits, when you're designing filters. So if we tinker this, move this to the side. So this code does actually have a function here, and all we're doing is counting from 0 and shifting the LEDs. So start the simulation. It's actually shifting each of the bits from one space, making it on low then high, least significant bit first. So here we've got an example for serial. Again, we've been using serial. So we need, at the beginning of a program, if we want to make a communication with a computer or another microcontroller, then we need to use the serial library, or another library that we would talk about later, or write your own. So serial is the name of the library. Then available is the link available. Start communication, end the communication, find somebody on the link, flush, clear the link through, send a float, send an integer, peak, set a timeout, serial event, read bytes until a certain time, read, write, print line, so print a single line or just print. Here we've got an example using the serial. Which is essentially we have a temperature of 0 in Celsius and Fahrenheit set declared outside. Pin mode A0 is input. 9600, that's the speed at which we are writing to the serial monitor. So 2, 3 and 4, pins 2, 3 and 4 are output. We've already declared A0 as input, and 5 volts and ground are your rails of power. So here we're saying the baseline temperature is 40. So above this temperature, that's when the LEDs will be activated. So we read the analog input and we map it between the value, take away 20 times 3.04 and 0, 0 to 1023, and we say we map it between minus 40 to 125. Then we convert it to Fahrenheit and we print out the value in degrees C, so the Celsius value, and the Fahrenheit value. If the Celsius is below the baseline temperature, we set all the LEDs to low. If it's between the baseline temperature, it's greater than the baseline temperature and less than 10 above the baseline temperature, we set the second LED. So the LED on pin 2, which is the yellow LED, to high. If the temperature difference is 20 degrees, plus 10. Oh, if it's between 10 and 20, we have the pin 3, so this LED and this LED are high and this one's low, and if it's greater than the baseline plus 30, all of them to high. Delay for 1000 milliseconds and then repeat. So 25 degrees C, so it's not above the baseline, which is 40. So how can I change this temperature? Well, if you click on the temperature, then it says extremely small there that it's 25. If I click here and I move it along, so that should now say 36, which it actually says 37, so it's fairly close. You want to do just over 40. So 49, and the LED on the right hand side has come on. You want to go between 50 and 60 now. Just below 60. No. There we go. 51 degrees is 2 LEDs on, and then the maximum is 3 LEDs on. So we've used the mapping function to determine or to show different temperatures for the input. So essentially do different things at different temperatures. Arduino IDE basic operators. So the general rule is in arithmetic, then you use a single character. So the equals sign, A equals B, plus, minus, times, divide, and modulus. So what's the remainder? 10 rem 3. Equals equals. So this is a comparison. So this would be used for a conditional statement. So if A is greater than or equal to 7, do this. While A is less than or equal to this, do this. While B is not equal to 5, do that. So that's comparison. Logics or pointers. So we'll talk about this in more detail later. Double ampersands is an and. Double or is, or pipe is or. Exclamation mark is not. Star, a variable name. So this is not where a variable is located in memory. It is a name of where the variable is located. And variable is how to get to the variable. ampersand. So a single ampersand would be a 1 and 0 equals 0. A single pipe or would be a bitwise OR. This is an exclusive OR. The tilde, or the small sinusoidal waveform, is a not. 2 less than arrows is logical shift left. So move everything 1 significant bit higher. This means logical shift right. So move everything one to the right. So down towards to the least significant bits. Assignments. So plus plus is if we had C equals C plus 1, C equals C plus 1, or C plus plus, then that means the same thing. Also, C minus minus is C equals C minus 1. If it's C plus equals 5, then C would be C plus 5, and then next time add another 5, add another 5, and add another 5. So whatever the number is. Same way, minus equals multiply by, divide by, and equals, so logical and, logical or. So replace the thing on the right hand side with the new value on the left hand side. These are the main Arduino Ide functions. Minimum, maximum, these are the mathematical ones. Absolute value, sinusoidal, cosine, tangent, power, x to the power of y. Map, I've just shown an example of the map, so you can say the minimum in, minimum, max in, and then map it to the min, out, and max out. So essentially it's scaling. Constrain, so you can remove decimal points. Square root, random number, random seed, milliseconds, microseconds, and delay in milliseconds. Flow control, we use if else, for, switch case, while, do while, break, continue, return, and go to. These will be explained in more detail in later on. Already mentioned this pinout diagram in the first lecture. So here we've got the output LED pin 13 because it's in the pink, and it's port B pin 5. So on port B it's 0, 1, 2, 3, 4, 5. That represents pin 13. 6, 7, 8. 6, 7. 0, 1, 2, 3. because we go from port B, port B 0 to port B 7. So as you can remember, we've got port B, C and D. So sometimes Arduinos can experience delay or latency. So dependent on the message size, then a number of milliseconds can pass for a particular instruction to be executed. Now, this is problematic with certain applications. Some applications it might not be. For example, when you're steering an autonomous vehicle, this would be extremely problematic. Whereas if you were sensing some temperature, then that might not be as problematic. So it's important to know these issues and design your project work or your work accordingly. This can be shown here as the rate of data transfer in kilobits per second, and there appear to be linear tendencies on an increasing exponential scale. This experiment has been done for several runs with similar results. So the other benchmarks are that certain built-in functions take time to execute. So digital read, for instance, takes 3.737 microseconds to run. The highest in terms of time is the analog read, not highest, but some of the ones to note are analog read, so it takes 112 microseconds, so 1.1 millisecond to read the analog pin, which again may be crucial. Random takes 137 microseconds. Dividing a double float by a double float is 80 microseconds. Compared to dividing a volatile byte is 12 microseconds, sorry. Digital read, digital write, 3 microseconds. The other thing to note on this slide is the delay of 1 produces, on average, a delay of 1004 microseconds. So that's just over 1 millisecond. Whereas a delay of 100 produces 99,975 microseconds, which is actually less than the delay required. The delay in microseconds of 1 gives just under 1 microsecond, 0.906, and a delay of 5 microseconds again gives a delay of less. So, and a delay. So basically what we're showing here is the delays are not accurate. Not when using Arduino Ide built-in library functions. So if you require high accuracy timing for your application, then these are not the functions to use. We will use these functions just to learn about the Arduino, and then I suggest you use C programming or even machine code, as previously discussed. This is just to remind you, I've already mentioned it before. So we have the pin mode 13 set as output in the setup loop, and we digitally write pin 13 to high and low and look at the fastest frequency that we can obtain, and it comes out at 121 kilohertz. If we write the same code for the switching the pin 13 on and off using C code, so port B, OR it with hexadecimal 20, that turns the LED in the 5th bit position on, and we NOT it with AND. So we use the OR here because if we OR it, then we're doing 1, 2, 3, 4, 5, 6, 7, 8. Because we're ORing it, it doesn't matter what's in these other positions. We're just making sure that that LED is on. If we're ANDing it with the NOT of this, so we'll be ANDing it with 1, 2, 3, 0, 1, 2, 3, 4. So anything that was contained in these positions, if it was a 1, will be remained as a 1 when we do this line. And here, anything that was a 1 will remain a 1 because we're ANDing. However, if it was a 0, it'll still be a 0. So the point of these two lines are we're only affecting the bits that's highlighted by the hexadecimal or binary number. And the others are unchanged because we are ORing it in the first position to turn that one on. And in the second line, we are NOTing it with the 20 to make this one off. Here we have 1, 2, 3, 4, 6. I'm just going to get rid of this one because we got an extra 0 there. No, we do. We need that one. So we do need that 0. So it's 0, 1, 2, 3, 4, 5, and we don't need that one. So we need an extra 0 there and get rid of that 0 there. Because it's port 0. Port 0, 1, 2, 3, 4, 5, 6, 7. Port 0, 1, 2, 3, 4, 5. And I've already demonstrated this to you last time, but there's the Tinkycad simulator for that test. Just going to add it on at the end. Tinker this. Start the simulation. These are a much smaller scale. (10 microseconds compared to 100 microseconds, and I can see that both LEDs look on all the time. However, by looking at the scopes, that they are clearly not. And the code for this Arduino is the C code, and the code for the original Arduino is the IDE code. Just a note about controlling motors. Here I have a H-bridge motor controller, and it's done in software here just by turning digital pins, 4 digital pins on and off. We will cover this in more detail in your laboratory. However, I just want to show you that here we have a motor controller H-bridge driver, which can turn these motors in these DC motors in both directions. It's the H-bridge circuit from yesterday's the first lecture. And what's going to happen is it's just going to show the code, and we're going to move each motor in one direction, then the opposite direction, by outputting data highs and lows to particular pins. And I'm just going to do that once. So I'm going to hide the code and zoom in. Start the simulation. So we're going positive direction, negative direction, positive direction, anti-clockwise. Okay. So that's it for this section.